Today we're going to look at hopefully 1.6, 1.7, and then we will move into, or sorry, 2.6, 2.7, and then we'll move into um, 3.1. I am pre-recording the lectures as I'm noticing more students are needing some more assistance with the homework. So we will go to a flipped model using these uh, PowerPoints may get a little tedious, but it'll get the information across. This way, on the videos, you can fast forward through the points where it's making sense. You can also turn up my speed. You can go up to like double speed. I know I tend to speak a little slower. That's what I do with a lot of my classes is I put it at 1.5 or 2 times the speed. I'm able to pick up the information that way. So we're going to work this way and see how this works. I will have this posted before class. You can review them, and then that will allow us time in class to actually work together through problems that come up. Okay, so um, let me get, okay, my pen's ready, and let's go. Let's see, this is going to work a little differently, I think. So here, the distance formula. Distance formula is to calculate the straight line distance between two places. Now, in city streets and stuff, if you're going through the streets, typically what we have to do is we have to uh, follow some kind of a path and um, going down the streets from one place to the next, or we could go north and then over. Um, But what we want to know is really what's the distance from an item from one point to another. And for that, we're looking for the straight line distance. And so this is kind of what we're wanting to find out. And there is a formula. You can kind of see that this makes, in this particular uh, drawing, makes a triangle. So it will involve the Pythagorean theorem. Call this side A, this side B. The distance we want is C. Excuse me. So we'll remember that A squared plus B squared equals C squared. We're going to see how all of this develops as we go through. Okay. So knowing the straight line, how do we do that? Yeah, clear these out. Um, so to get this straight line, we're going to need to use the Pythagorean theorem, right? So we go 3 miles, the house is 3 miles down to the vertical tower, 2 miles to the east, we get to the tower, um, or is that to the west? I get confused myself sometimes. So um, the house is to the east of the tower. Anyway, 2, 3, there's 5 miles uh, that it would take us to get, basically to drive there. But what is the straight line distance? Well, if we remember the Pythagorean theorem, we can square the 3, square the 2, um, and then we'll be able to calculate that distance. 3 squared plus 2 squared, so that's 9 plus 4, which is 13. Square root of 13, plug it into the calculator, it's 3.6. So the distance between the tower and the house, straight line, closest distance is 3.6 miles. Just a little bit outside a reception area. Now that's a tenth of a mile. Maybe you'd get some reception, but evidently it's saying not good. Um, the limit of good reception is 3.5 miles. So there we are. Um, and that's how we're going to do it. Now, what we're going to see is we can calculate these changes in x and the changes in y, the distance x and y, um, simply by subtraction, right? Because if we know one coordinate, we can get to the others. So that's our next step is when we have like coordinate systems, how do we calculate the distance of the x and the distance of the y? We're going to use the same process um, where we find that difference and then we square it and we find the other difference and square that. Um, And then as we add those two together and take the square root of it, what we get is we get the length of the hypotenuse of the triangle. Okay. So let's get these out of here. Um, what we want to do is be able to define the variables so that we can say, okay, this house was not good, but where are the good houses? So we're going to say, maybe it's like a circle around here, 3.5 miles. So we need to define streetwise how that is, because again, how I guess a house could be on this side of the street, but typically there's nothing in the middle because you need streets to access the buildings. So let's figure out where could there actually be houses that will have good um, reception. And so we take our base and we call that the horizontal distance, and we take our vertical distance and we call that V. And what we're going to see is that once we calculate H and V, we square them, add them together, and take the square root, and that will give us our distance using the Pythagorean theorem. Okay, so once we have our H, the distance for any house is their horizontal distance from the tower plus their vertical distance squared towards the tower, take the square root, and that will give us our distance. And what we're going to do is we'll set it up so that our distance is less than 3.5, and that's going to give us the circle where we have good reception. So they also tell us that we have another cell tower located at some other point, H1, V1, to find a formula to determine the distance of any house from that cell tower. Okay, same thing. Distance from this one, again, what we defined is that house would be H and V away. So to get to the next cell tower, because maybe it's covered by another one, we've got this coordinate here. What we're going to do is we've got two coordinates, so we're subtracting, right? So the second cell tower, H1, V1. Okay. And what that gives us is, what we're going to see is if we've got some coordinate, in this case they give us negative 2, 4, we want to find how could we calculate this circle around, and in this case we could see it has 1, 2, 3. So we're now saying good coverage is 3 miles away instead of 3.5. So we've got a cell tower at negative 2, 4. We've got a point at x2, so some x value, but the y value is 2. Okay, so the y value is 2. And we're told that it's southeast of the tower. So south be down here, east would be here. So if it's going to have good coverage, it better be about right there, So the way we could figure it out, we know the distance has to be 3 or less. So this is kind of giving us the boundary. And what we've got is the point, the coordinate of the point is x. The coordinate of the tower is negative 2, so we subtract those to find that distance, right? X minus minus 2. We're going to square that because that's going to give us, that's part of the Pythagorean theorem, right? This is our a squared, and this is our b squared, and this is our c squared. Okay, and then 2. Since we know the y value, we can subtract the 4, so 2 minus 4. What we end up with has been shown out here. We do the math. X minus minus 2 gives us x plus 2. 2 minus 4 is negative 2. We square both of those, so that's going to give us x plus 2. This gives us 4. Negative 2 squared is 4. They subtracted it from both sides, giving us, solving this to get the 9 to be 5. And then now is the time we take the square root of both sides. We could have done it earlier, but we're going to have this variable in here. So they take the square root of both sides here. Square root of 5 is equal to x plus 2. And then what do we have to do? We have to subtract 2 from both sides. So, and then what they did is they moved the x over here. Now I mentioned earlier, oftentimes we get more comfortable with having the variable on the left side. So I would have just maybe x plus 2 equals square root of 5. Then subtract the 2. The reason I don't put the 2 behind the square root of 5, because then it's kind of confusing. Is this 5 minus 2 all the square root? So because the back end is kind of open, sometimes I'll put a little, okay, that's the end of the square root. But the way to do it is kind of, okay, subtract 2, which means we're adding square root of 5. So that's how they got that. And so now we know the x coordinate. It's negative 2 square root of 5. You do the math, it's a slight decimal, and you're going to find out, yes, graphically, it's going to be right here. So south of it, that's exactly 3 miles away. Y is going to be 2, so it's going to be on here, and it's going to be on this circle here. So it would be this particular house would be a distance of 3 away. Okay, which is 0.236, and that looks about right. It's less than 1. It's about a quarter of a way, and that graphically is looking about right. So now we've got this same cell tower 3 miles away. We want xy to be any point on the surface, the distance to the house from the cell tower located. Clearly define any variables that you might use. So what if what do we need to know? Well, x and y could be anything this time. So last time x was varying, but y was 2. So it's kind of going to give us an overall formula that we can work with. So x and y are the coordinates of the house. For it to be on that boundary, it's got to be exactly 3 miles away. So, but if we just want to know the distance, we could call it d. Okay, so it's going to be x minus the x coordinate of the cell phone tower and y minus the y coordinate of the cell phone tower, just like we did. And then in this case, we'll take the square root. So this gives us a way that give me the x and y, we can calculate directly the distance for any house in here, whether it's on the boundary or not. Now, if it's not on the boundary, it might be more or less than 3 miles away. That's fine. And again, it will kind of, any coordinates, visually we can see, okay, the result for this particular house, that's at, what's that? That looks like negative 2, positive 3. That house will certainly be less than 3 miles away. So we can see visually what it's going to be, but we can also actually calculate what we end up with. Okay, so that's using the Pythagorean theorem. We get basically get a equation for a circle, and are able to calculate straight line distances. So now talking a little bit more about distances, absolute value, and inequalities. This is going to be more of a two-dimensional measure, but absolute value gives us the distance from 0 on a number line. So we're going to work through a few of these. I guess before I go on, let's see, do I want to do that now? Yeah, let's take a look. Let me, some of the lessons, again, while you're not required to do these, if you feel ready, you can go ahead and go. Notice the lessons are still open. They're in review mode. Don't worry about scores. We'll look at the homework. But they provide some, again, this is 1.6, so we were looking at the distance formula. We start looking, they got some pictures here, what the distance in the x direction is. It's the horizontal distance, right? And the distance in the y direction, if we have a coordinate, that's the distance from the x, from when y is 0 up to that point. So it's a vertical distance. We're going to get some things we can play with, and we can kind of see, we can change the y value. As I change my y value, that's the distance of the point, the height of the point. If I change my x value, I can see the x value changing, and so it's sort of the horizontal distance gets bigger or smaller. And the advantage of going through with these applets is always that your mind is actually now getting to play with it. You might say, yeah, that makes all sense, and I sort of got that. But sometimes just the fact of doing things, it gets your brain to work in a different way. You're getting some hand-eye coordination as you're thinking through things. You're seeing it, and it records it in a deeper mode. So that's why I highly recommend coming into these. These will help you gain that understanding more deeply. Okay, so don't worry about having to do it, but take your time to go through these. Now this is not a difference, but you could say, okay, horizontal change. Well, the nines are the same, so that's not changing. All I got to do is subtract the x's. So 10 minus 6 is 4. 1, 2, 3, 4. I can see it, and I can see, okay, yeah, subtract the 2, and it's a distance of 4 away. Now, if you did 6 minus 10, you get negative 4, but you say, okay, distance is always positive. So 6 to 4 is 1, 2, 3, 4 units. And then we've got this one where we can actually plot things. So they want us to, and again, the idea behind this is it's getting you to work in different ways. So 3, 2, 3, 2, we plot that, and then 6, 2. Okay, that's just a horizontal line. And again, it might seem like this is, you don't have to submit or anything, but once you do that, it helps mentally really connect. Okay, that's a horizontal line. That's what's going on there. I see that the x's are not changing. Sorry, the x's are changing, but the y is not. So that gives us a horizontal line. And again, you can have a little applet where you can stretch things out, and you can see all that is changing is the x coordinate. X would be x here, okay, right? The y coordinate is staying the same because we're horizontal. Okay, some activities to go through. Again, you'll see some of these into the homework, but you can see to figure out the horizontal change, all we got to do is subtract the x values and go through there, and it'll hopefully make some sense. Then it does basically the same thing. Go with the vertical distances. That's our change in y, and you can see x's are staying the same this time. So 9 minus 4 is 5. 1, 2, 3, 4, 5. I could count it or I could calculate it. So those are good things to follow through. And then a applet to draw. Again, you can see it's going to be vertical because the x's are the same. 5, 5 and 5, 9 up here. There we go. You see it and move forward. Okay, and then we get into the Pythagorean theorem. So, okay, yeah, we talked about that. Yeah, a squared plus b squared equals c squared, and we see how that works with some various values. And then we can draw triangles. And again, sometimes it seems to belabor it. 8, 2 is here, and 8, 10 is up here. But it does help some of us, especially if you have a tendency to transpose numbers. This helps the training to say, okay, the first coordinate is your horizontal, it's your x. Second coordinate is your vertical, it's your y. You see it done, and you actually do it a few times. It's very helpful. And then we could say, okay, what's the horizontal leg is down here, so that's 1, 2, 3, 4, 5. Or we could have said 8 minus 2. I say, wait, did I count that right? This should be 6. 1, 2, 3, 4, 5, 6. Yeah, so slow down a bit and go through and do that. And again, another option to draw the polygon, draw the triangle, see it, practice, and go through there. So again, a lot of activities to try on, submit them, and you can see this is fine that it's in review mode for right now, and that's all it needs to be in. This formalizes what we came up with from the lecture, that the distance between any 2 points, we can subtract the x coordinates of the 2 points, subtract the y coordinates of the points, square both of them, and then take the square root. Now, if it was horizontal or vertical, all that ends up happening is we get, one of the distances is 0. But when it's at an angle, this will give us the straight line distance between the 2 points. Kind of like what we were talking before, average rate of change, so this would be the fastest way to get to some place. And again, some points here, and then we can calculate their values between them. Um, Lots of practice, and then you think about what you learned. Okay, so that's for 2.6. I'm going to leave this one. 2.7, I think I'll change back. We'll take a look at the applets that you should look at for 2.6, 2.7, and as we go through, but I'll kind of continue with the lecture. But if you go to the lessons, you'll see applets for 2.6, and we'll just do a review at the end of how you should work through those. So the absolute value, um, this is giving us basically a plus or minus. Absolute value just says value away from something. So a carpenter needs to cut a wood board to a length of 7.6 inches with a tolerance of 0.1 inch, meaning the actual length of the cut must be within 0.1 inch of 7.6. So you could think, okay, it could be 7.7 or it could be 7.5. So let X represent the actual length of the board after cutting. So what are possible values? So yeah, 7.5 or a little bit larger, 7.7 or a little bit smaller. All of these would work, right? They're all within 0.1 inch. And if we come on to the number line, we see the 7.6 is going to be represented by a line from 7.5 up to 7.7. Those will all work. There we go. It can be a little bit shorter. It'll still work. I don't know, put some putty in there. It could be a little bit longer. Just use a hammer, squeeze it in, I guess. But, you know, it's hard to get exactly 7.6. Okay, so all of these will work. This is the idea of absolute value. What we're doing is we're getting all the values that are 0.1 inches away from 7.6. So any board that's from 7.5 to 7.7 is a usable board. Cut off too much more and it's no longer usable. So how could we write this with a mathematical statement? Well, we could say X has to be any value. And again, X, we define X to be the length of the board, 7.5 to 7.7. Any board in this length will fit our needs. Close enough. Okay. And the difference, 7.6 is like the ideal. So the 0.1 is the error we would make. And most items, whenever we measure, there's a measurement error involved. Okay, again, desired board length, and then an error of plus or minus up to 0.1. Smaller errors are welcome as well. Okay, so we look at it either, whichever direction. So if X is if the cut is bigger than 7.6, then it's the amount minus 7.6. It's always thinking of it as a positive amount. Okay, so we can look at it this way as it's the absolute value, because error is not really negative or positive. It's, we can go that direction, but this is still an error of a certain amount, same as the top. So it's an error of 0.1 below, error of 0.1 above. When we use absolute value, it takes off the sign, makes sort of absolute. It's a value without a plus or minus sign. Actually, makes it have a plus sign, right? So when we have an inequality, what we really started off with is that x minus 7.6 has to be between. Again, this is when we're looking at the error, it's between negative 0.1 and positive 0.1. Want that error. And we could also think of, if we do it the other way, 7.6 minus 0.1, and again, it just is the error above or below. So notice we kind of switch them back and forth. It's also in there. So we can represent this simply by taking the absolute value of x minus 7.6 or 7.6 minus x. We can get kind of a sloppy of which way we're subtracting, because we're just going to ignore the sign. If you take 3 minus 4, you get negative 1. If you take 4 minus 3, you get positive 1. If you ignore the signs on those, you've got the same value. And that's the idea here. Okay, so with absolute value, we can ignore the sign, but we'll see how we go about solving these. Okay, so write a mathematical statement that represents actual board lengths. So again, what we were representing there were the amount of the error, not the actual board lengths. So this time, we're representing that x has to be that the kinds that would not work anytime x was less than 7.5, we couldn't use it, or if x was greater than 7.7, we couldn't use it, right? Carpenter needs to cut a wood board to length of 7.6 with a tolerance meaning. Okay, same problem. But that's the outside. So these are the types of boards we would have to throw out. Now, if you cut it way small, again, 7.5 is usable, 7.7 is usable, so those are kind of the boundary points, and that's why that's an open circle. 7.7 is one we could use, 7.5 is one we could use, so it doesn't have the equal sign here, and we represent that with an open circle. Okay, so what are some values of x that meet the constraint? Suppose we want to choose an x value within 4.5 units of 16. So you subtract 4.5, you add 4.5, and any of those numbers in between. So numbers like 12, that works. 16 works, you could be right at 16. And 20.4, so 4.5 plus 16 is 20.4. That still works. It's within 4.5 from there. So then how do we write a mathematical statement? Well, we want 16 minus x or x minus 16 again. Either way, but we want this error, this amount, this result, when we subtract it, to be greater than negative 4.5 or less than 4.5. Okay, what we can do is add 16 to both sides, and what that gives us is the values, right? So add 16 to 4.5, you get 11.5, add 16 to 4.5, and you get 20.5. That's what x has to be between. So represent the possible values x on the number line. And you'll have some applets where you'll actually be able to draw this, but we can see the 16, 4.5 above, 16, 4.5 below on the number line. Any of these values are usable. Okay. Say we want to we want the change in x away from 5 to be positive, but no more than 3. So this is a one-sided. We want it to be a positive, but no more than 3. The change away from 5. List some values of x that meet that constraint. So we could be 7, 5.1, 7.8, but we want to be on the positive side, right? Something less than 5 isn't going to work. So we want x minus 5, because x is on the positive side. X is bigger than 5. We want this difference to be between 0 and up to negative 3. Okay. Now we want to change in x, so in this case, it's not actually going to be equal to 5, because we want some kind of a change. So we can see that 5 is not included, but we can go all the way up to 8, including 8, and still just be 3 units away. Draw it on the number line. So we could go from 5 all the way up to 8, but we don't include 5, I guess, because that's not really considered a change. Change of 0 isn't really a change, is it? So if we're still at 5, nothing's happened. We've got a change in the positive direction. Notice we don't use absolute values here. Absolute values would give us also below. Okay, at least 4 units away from x, at least. That means up 4 or more. So what you're going to see is there's kind of, there's two things. Sometimes we want to be within 4 miles of where we work or something, or where we go to school, so that our commute is low. Sometimes we want to be at least 4 miles away from something like a smelly factory or something. In Oregon, there was a paper mill that we lived too far from, and I was 13 miles away from it, which was usually okay, unless the wind changed directions, and then you smelled the paper mill. So anyway, we go to negative 3, And in this case, we want to be 4 units away at least. And so we're going outwardly. And so how do we write a statement that makes this work? Well, x, we can see here, x is either going to be less than -7 or x is going to be greater than 1. You really come up with that by plotting it on the number line. Mathematically, we could say, since we want to be away from x minus 3, right? Remember, when you're calculating change, it's you subtract the 2, so it would be x minus minus 3. So we want that to be, we want the result to be either -4 or +4. And this is going to be the distance between the two. Okay, so we could list that as an absolute value. Absolute value of the distance between x and -3. Let's back up. The absolute value of the distance between x and 3 is going to be greater than or equal to 4. So this is, the paper bill is at -3, and we want to stay away from it, something like that. So the definition of absolute value is it's a number that's always going to be positive, and it represents the distance that you're, and when you have an equals, you're exactly x units away from some point. Okay, so C is how far away you are exactly. If we do a less than, this is going to represent thinking we're less than that distance. So this is going to give us a circle around the point H that is a distance of C or less. And then if we want greater than, this is going to be distance that is at least C units away. X is something that is at least the distance of C away from H. Okay, so that's how that's going to work. So looking back, we got the absolute value. This is less than or equal to, so that was, we're trying to get close. We're less than 0.1 from 7.6. This one also, we're less than 4.5, a distance of 4.5 from 16. For 4b, we're greater than, so we're at least a distance of 4 from -3. Okay, let's see, we're almost getting to here. So we've got Jamie doing a model airplane. Instructions say the best final weight is 28.5 ounces. However, as with everything, we can be higher or lower than 0.6 without affecting how it flies. So how do we represent this? Again, we're seeing probably going to involve an absolute value at some point, but we could also think, okay, 0.6, will we add and subtract it? That gives us our boundaries. The plane can weigh anywhere from 27.9 up to 29.1 and still be acceptable. How does this look as an inequality using absolute values? So again, we're talking that the weight, the distance from the actual weight and 28.5 has to be less than 0.6. Okay, and this absolute value means it can be above or below. And so we can also just list that as W minus 28.5 has to be between -0.6 and 0.6. Okay, so this is a look at the distance between, or the error in the measurement. Up here, we're looking at what are possible values. Okay, so what's the meaning of x minus 5 less than 2? Think about it. It means all the values of x that are less than 2 away, not equal to 2, just simply less than 2 from 5. And again, the negative is always there because of distance, so this is distance away from +5. The values of x must be at least 2 units away from 5. Must be less than. So sometimes I don't see the words when I'm reading. So represent all values. Okay, so that means, let's see, if we're less than 2 away from 5, so we could be up to 2 so that'd be 7 and 3, but those endpoints are not equal. So notice we've got 3 and 7 themselves are actually not less than 2, they're exactly 2. So we write that with the number line with the inequality. Um, and we could do the same thing. It's negative 2 to 2. That's where the error has to be. So x minus 5 is between those two. Now, you'd also be correct if you said 5 minus x, because it just would produce other ones. But x minus 5 or 5 minus x would work. But it's if we get consistent this way, we can look, okay, we're at 5 is sort of the center, and x is some value that's going to keep us in this interval, keep our error down to plus or minus 2. Okay, so what's the meaning of this statement? Notice 1 is above, 1 is below. So this is distance away. So this is a distance at least. So we want to be 5 miles away from positive 1. We want to be on the other side also a distance of 5 away from 1, positive 1. So we can go to the negative side or the positive side. But x must be at least 5 units away. Okay. Now we could write this with an absolute value, and then this is sort of how we go about solving it. Okay. So we can just think that we're trying to stay away from positive 1. We want to be 5 units away. So that's negative 4 up to positive 6, and that's the number line we get. Using absolute values, positive 1, W is 5 or more units away. Okay, so all the numbers of x distance from 6, no more than 7. So again, the distance from 6, so that's what's going to be in here. So it'll be minus 6. So there's all, because this is calculating a distance, it's always subtraction. And it's saying we're staying 7.5 units, no more than that, which means equal up to that amount or less. All numbers are whose distance is negative 2 from the unit, so whose distance from negative 2 is more than 1 unit. So negative 2 is our distance, so minus minus. Again, we could just write that as our plus 2, but just remember if you got a plus there, we were supposed to be subtracting, so we're at negative 2. And the absolute value tells us we're at least 1 away, so we add 1 and we subtract 1. Okay, and then for each of these, we'll just kind of go through. Yeah, we're at 11. We want to be less than 6 away. And so that's giving us this. And we can basically add 11 to both sides of this, and it tells us what numbers actually work. 5 to 17, as long as we're in that range. And again, we could graph it. We see that the 5 and the 17 are not included because those are where it's actually equal. But we want to be less than that amount away. Okay, absolute value, y plus 7, so we're at 7, and we want to be more than 1 unit away from it. So the values of y that are at least 1 unit away. At least includes the equals part. Okay, so y plus 7 is greater than, or y plus 7 is less than negative 1. So we break it up that way. We can solve it, subtract 7 from both sides, so we've got to be between negative 6 and negative 8. See how that works? So we knew we're at negative 7, we want to be 1 away or at least, and so we get both sides. Looks like this, and because of the equals, we get a solid dot. Okay, we're going to see that also translates when we use interval notation as a bracket rather than a parentheses. Okay, here we're going to, again, we would use parentheses because the endpoint is not included. Again, we're at the x value of 3.3, positive 3.3, and we want a to be some number that is at least 0.8 away. Okay, so this statement is to be greater than 0.8 or less than negative 0.8. Sometimes if you kind of figure it out and do the number line first, it makes more sense. But so we add 3.3 to 8.8, and we add 3.3 to negative 8, and we get our two endpoints And again, the endpoints are not equal or not valid, so they're open circles. And again, we go to the left or to the right because that's the inequality. So we're either wanting to stay away from someplace or we're wanting to stay close to someplace. This is greater than, we want to stay away from it. Okay, less than, we want to be close to it. So we're going to see um, we want to be close to -2, um, within 5 units of -2 at least. And so again, we can set those up. A lot of examples to kind of go through. Um, we could subtract 2 from both sides, and that gives us our endpoints. And so you can kind of see how the method of solving these as we go through, whether it's less than or whether it's greater than, and what that's going to look like, whether the endpoints are included. And again, those would be brackets if we used it as an interval notation. Um, and so, let me just, what's that going to be here? Interval notation would be from -7 to 3. The previous one, we would have parentheses because it wasn't included, but this is with the included one. If you have open circles here, because you had simply less than without the equal to part, then we're putting in -7, 3. So those are the two ways to write it. One's included, one's not. Then again, the included always gives us a bracket. Not included gives us a parentheses. Okay, so just kind of covering interval notation at the same time because that's going to come up. And you can kind of see these just keep going on. So we could think of this as absolute value, and we could think of distance away from 0. And so we could just list this as absolute value of x, couldn't we? So it's everything that is a distance of 6 away from 0. So those numbers would be 6 or -6, 3 or -3, not including, right? This one doesn't include. Equals is exactly. So we look at, whether what that symbol in the middle has a big meaning. X equals c, so this is going to be x is going to be plus c or minus c, right? And that's the distance from 0. So just remembering, we're still talking distance because it's really x minus 0, but it disappears because subtracting 0 does nothing. This is going to be, we want to be, at least greater than or equal to this distance. So x is greater than c, or it's less than -c. And remember, we have that because the middle part is not included. We want to be at least as far away. So there's kind of an opening in the middle. We need to list it as 2 inequalities. X equals 4. So again, we've got the equals, -4 or +4. And that fact that x is, whatever x is, it's exactly 4 units from 0. So yeah, -4 and 4. Plotted, they're both just 2 points. Cool. Absolute value, but now we've got an inequality. Remember, it's less than, so we're going to want to be between 0 and 5.5, no more than 5.5 away, so -5.5 to 5. And when we graph that, since it's included, we have the point there, and then we're including all this stuff in the middle. We'd like to be no more than 5.5 miles away from this 0 point, which might be work or school or someplace we want to be close to. This one, we want to be far away. We want to be at least 3 units away from 0. Okay, so the same thing. We need to use 2 answers, 2 inequalities to be more than 3 away and less than -3. Okay, and that looks like this. And since it's not the equal, the 3, the boundary point is not included. And just to kind of show you that, let's take a look at what that might look like as interval notation. So this part is going from -infinity, right? We can get as far away as we want, all the way up to -3. And then we use this little u for union. It indicates that there's a space at the middle that we're not talking about, but then once we get past that, we get to the other side, +3 to +infinity, we can include that part. So that's their interval notation, which will be coming up and we'll be using throughout the course. Let's clear this out. And I guess we're done with this one. So I'm going to pause things for now and move into the next um, lecture um, on the absolute value. In the value going into the lessons is that they have these applets. And so they want us to do something. We're cutting a board 9 inches can be up to 0.3. So 9, there's 0.3 above. And here's 0.123 below. So you can kind of see it. We're drawing it. You got the values in here. And do the parts you need, but I think the most valuable parts is actually doing the drawing, the applet type things. Um, gives us some ideas. There's some training in here. Again, it should be helpful, and maybe some things you want to add to notes or something. Um, again, a distance of 0.3. It's really just highlighting what we went through, but this gives you an opportunity to sort of work through it first. Some of these things you'll do in the homework, but sometimes the homework doesn't have these applets in here. So all possible numbers that are less than 2 units away from 5. So here's 5, 1, 2. I'm going to do that with an open circle because we don't want to be exactly 2. We want to be less than 2. So there we go. Use an open circle to indicate that we don't want to include the endpoints. So they give us some help here of why that's an open circle, because we're strictly less than. We're not less than or equal to, or no more than 2, right? No more than 2. That would include 2. All right. We can see we break up absolute value. It's either the positive or the negative. That's really what's telling us. And it's distance from 0, so we're highlighting it here. We've got the opportunity to use the applet and go forward. Graphing, again, more graphing. Highly recommend you go through and actually work through each of these with the applets. At least draw the number line. And then you could just check that part. It'll tell you which parts are correct or not. Here's an absolute value. So we're at positive 5, right? And we want to be less than 2 away. So what does that look like? Less than 2. There's 2 there. So we can do it this way. And let me see, even though I'm in review mode, let me see what happens if I just submit it. So I could be 2 below and 2 above. Let's go ahead and submit it, see what it does. I know I didn't do all the stuff, but it does tell me that my graph is correct. Okay, so I could have put these answers into. Just helpful. It will go through. It's not recording scores, but it doesn't need to, because all you have to do is the homework. Okay, so keep working through it, but come back to these. I believe they will help you learn. And what I want to do is motivate you to think about the learning as being the most important thing, and not thinking about accumulating points. Hey, I did my work, I got my points, so that means I'm done. Well, not necessarily. Um, you need to learn the material so that you can apply it and that it has value in your life. You take it away, you take something with you. If you did it and done it and got your points and that was all you got out of it, those points are in, try to spend that at the grocery store, right? Um, so what, you got an A. If you didn't learn anything, it's really of very little value to you. So I hope that helps you to focus on um, the learning aspect and this method of going through and actually graphing things, doing it. It makes the brain work in a different way because we're actively doing something. We're drawing a picture. It's a different way. It gets our left and right sides to work together better, interactively, and we'll remember things because we're using our vision, our eyes. We're seeing it. We're thinking it. We're doing it all. And maybe if you're like me, you talk to yourself as you do these things. You're also hearing yourself talk, and you're talking. There's a lot of things going on. It makes for really deep learning. So we'll keep moving forward with this. Let me go ahead and stuff. And thank you very much for listening.